Good morning. So, today we will continue our discussion on thermionic energy, material and devices. So, what we have seen in the last two classes that thermionic emission is a physical process by which electrons are emitted from any material. There are some other electron emission process also which I mentioned, and then what we have seen, what are the essential requirement of a good thermionic emitter, and what are the essential properties of the material which control a better thermionic emission from any material. And then we have seen that what are the typical components when we make a thermionic energy device or thermionic converter, and what we have seen that generally the thermionic energy device, it is in diode geometry. So, we have an emitter, that is cathode, and a collector, that is anode, and then when emitter is heated by some source of it, it emits electron by thermionic emission process, and then it gets collected to the collector, and that when this electron is returned, we have to pass it through a circuit outside having a load in that circuit, and the power is generated there. Okay. And then we have also discussed about the how to define the efficiency of a thermionic emitter or a thermionic device, and then we have seen that what are the important materials when we consider the emitter material or cathode material and the collector material or anode material, and what are their essential properties. So, we have seen that as far as the cathode is concerned or emitter is concerned, there are some very good materials which people have done lot of research, like refractory metals, oxides, hexaborides, etc. Those materials have some of the essential properties which are required for a good thermionic emitter, and they are being regularly used. Okay. Similarly, for the collector material. And then we have also seen what are the heat transfer process in a thermionic generator, okay, and some important application of thermionic devices. Now, today I will review this topic again with some questions and some important points will be discussed in today's lecture. So, let me ask the first question: what is the difference between thermionic emission and field emission of electron? So, if you remember that I mentioned that there are different electron emission processes. One is thermionic emission, which is very popular because a lot of work have been done in thermionic emission, field emission, then photon induced emission, secondary electron emission, etc. So, when we consider thermionic emission, it is basically an emission which is driven by heat energy. So, thermionic emission is an emission which is driven by thermal energy. Okay. So, when we keep some thermal energy to one of the electrode, that is cathode or emitter, these electrons are ejected from this material by thermionic emission process, okay, and then it is collected at the collector kept at certain distance. Okay. But when we consider the field emission of electron, the field emission of electron is that we do not apply any heat so we can say that it is a cold emission process. A cold electron emission process, that means there is no heat applied, but what is applied is an electric field. So, we can say that it is field induced process. Okay. So, in thermionic emission process, when electrons get energy from the heat source and then they start moving, and some of the electrons which can cross the work function of the material come out, that is the thermionic emission process. But in field emission, as there is no heat energy, it is only this electric field induced effect. So, what happened, the electrons, suppose the electrons from the Fermi level, they actually come out by a process which is quantum mechanical tunneling. So, what we have discussed, if you remember that if I consider a potential well, electrons are in a potential well. Okay. If we apply a thermal energy, they can cross it well and then they come out. But if we do not apply thermal energy, but we only apply the electric field, then the potential barrier is modified and the electrons come out through this potential barrier by quantum mechanical tunneling process. Mechanical tunneling. Okay. So, this is the basic difference between thermionic emitter and field emitter, or thermionic emission and field emission. So, when we consider thermionic emitter and field emitter, generally thermionic emitters are, you can take a flat cathode, okay, or say a filament, but for field emitter it is always better to take sharp emitters, because one is to generate high electric field at the tip of the sharp emitter. Second question is, why thermoionic current density depends on work function of the metal and on temperature. Okay. So, you remember this Richardson-Dushman equation, where it has been shown that the current density of a thermionic emitter depends on both work function and the temperature. So, it is straightforward that what is the work function? Work function is basically the energy if this is the Fermi level and this is the vacuum level, the energy required to take one electron from the Fermi level, okay, to the vacuum level. So, that is work function. So, it is clear that if the work function of the material is high, it will be difficult to to take out one electron from the Fermi level. If work function is low, then the emission will be enhanced. Okay. So, that means the current density increases if we decrease the work function. Clear? Okay. Now, if we look at the temperature effect, temperature is again, the temperature is something that when we give more heat energy, more temperature is generated, and if more heat energy is given, then the electron's kinetic energy will enhance. Okay. So, they get more energy from the thermal energy and they can easily cross the work function or the barrier, or they can easily attain an energy and can come out by crossing this work function. Okay. All right. So, that means the current density increases when we increase the temperature. Therefore, it is an essential requirement of a thermionic material or thermionic device that we have to keep the work function low and the temperature high. Let us see the next question. How thermionic electron source is used in electron microscope and X-ray source? These two are very popular, the application of thermionic sources, because we all use electron microscope in our laboratories and also X-ray source in our laboratories. Okay. As far as the researchers are concerned, these two applications are very common, and that how these thermionic emission source is used. Okay. Suppose you take an electron microscope, say transmission electron microscope or scanning electron microscope, we have an electron source, okay, or electron gun from where electrons are actually emitted and they are going towards the different section of the microscope. Okay. So, the electrons emitted from a thermionic emitter, which is the source at the top, they actually cross through electromagnetic lenses, they get focused and then they fall on a sample. Okay. And for secondary electron emission microscope or scanning electron emission microscope or for transmission electron microscope, so these electrons interact with the sample. Okay, and they can produce image. Okay. So, there are different techniques how they produce the images. This is not our discussion here, but what we see that the electron gun or the thermionic electron gun is the first component of an electron microscope, and the electrons generated in the thermionic electron gun are actually the most are the probe for creating these images in SEM or TEM or electron microscope. Okay. So, now how they used in X-ray source, we all know that how X-rays are produced. Again, for X-ray we need again a thermionic electron gun, okay, and then electrons are emitted from the gun. All right. So, this is an E gun, I should write thermionic. Okay. So, electrons are produced and then they strike any material which you want to generate X-ray from, okay, say aluminum, say copper. So, electrons hit, they are bombarded and then the X-rays are emitted. There are two different X-rays. We know that the X-rays are could be characteristic X-ray. What are characteristic X-ray? Characteristic X-ray is that when one electron jumps from one energy level to another energy level, okay, then it emits a characteristic X-ray. Okay. We all know that what are the characteristic X-ray like K alpha, K beta, we are aware about this nomenclature of characteristic X-rays. And also there are a continuum radiation of X-ray. Okay. This happens because when electron goes inside the material where it is bombarded, it also gets decelerated because it is passing through that material. Because of the deceleration process, there is a continuum X-ray source, X-rays are produced, X-ray photons are produced. Okay. So, that is a process which is known as Bremsstrahlung, and this is continuous X-ray. Okay. Typically, when you record these X-rays which are coming out from these sources, you will see that there is a continuum background and then there are some characteristic peaks. Okay. So, these are characteristic X-rays and this is a continuum background. Okay. This is, I can write some energy of X-ray photon. So, this is our typical X-ray source which we use in the laboratory. But what is the importance of thermionic process there? Because the starting point is this, that is electron gun, which are thermionic in nature in most of the cases, okay, for production of X-ray. Now, we come to the next question. What are the physical quantities those contribute to the voltage generated in a thermionic converter? So, it is a very important point, because once we talk about the converter or the energy device, we have to produce voltage. Okay. So, if we look at the configuration again, which I have discussed, that we have a hot emitter, okay, and then we have a cold collector, all right. So, this is the heat input and the electrons are emitted by thermionic emission process and going towards the cathode, and there is a heat removal process here. Then these electrons are directed towards this path, it is crossing through a load R L, okay, and then electrons are again back here. By this process it generates a voltage. So, if you again look at that in the energy scale, how can we define this particular phenomena? So, this is the Fermi level of the emitter material and this is the Fermi level of the collector material, okay, and this is the vacuum barrier and this is the phi or the work function of the emitter, and this is phi c, this is the work function of the collector. So, phi e is the work function of the emitter, phi c is the work function of the collector, and electron moves in this direction, and this difference, this particular difference you can see, which are actually this current when it is going back dropped in the load resistance, actually gives us the output voltage. Okay. So, this is a way we define the output voltage, and you can write very simply that E V out is equal to phi emitter minus phi collector. Okay. So, the voltage output of a thermoionic device depends on these two work function of the emitter and the work function of the collector. If the work function difference is large, then the voltage generated is higher. Define efficiency of a thermionic converter, how it can be enhanced in a typical configuration of thermionic generator. Okay. So, I have already discussed the voltage, how much voltage one can get. Okay. So, when we come to efficiency, efficiency is generally, how do we define efficiency? Efficiency is always the power generated by some quantity which is causing that. Okay. Suppose we consider the efficiency of a solar light, the power generated and the solar power density. All right. So, similarly here also we defined as efficiency as power generated or power density by the thermionic device divided by the heat flux. Okay. So, this is power density So, I can define power density is equal to current density into output voltage, all right, and I have already defined output voltage. Okay. And current density we can again define from the Richardson-Drushman equation. So, all the quantities for the efficiency are the known quantities. All right. So, again this current density depends on the work function, it depends on the temperature as per Richardson-Drushman equation, and then all these quantities actually contribute towards efficiency. Okay. And how it can be enhanced? If you want to enhance efficiency, you have to enhance this quantity. This is a very important quantity because it will enhance the output voltage. Okay. Clear? And you also have to enhance the current density. That means you have to generate now, if your work function difference is fixed, then you can increase the temperature in order to enhance the emission and the efficiency of the thermionic converter. Next question, what is the space charge effect in thermionic device? How it can be minimized? Okay. Space charge, we can understand the charge which is generated in a space. Okay. What is the space here? It is basically the space between the emitter and the collector. All right. So, when electrons are emitted from the emitter, okay, and they are collected in the collector, okay, a space charge, that is sheath of electron, can be generated in the space here. So, this will actually hinder the flow of electron, all right, or they disturb the flow of electron. Electrons will be repelled back from the space charge. And space charge effect is always, it is always there whenever a charge flows from one particular plate to another particular plate. All right. So, in order to minimize this space charge, one has to do something. So, generally what people do, they put cesium vapor, okay, and when they flow the cesium vapor inside or in between the two plates, they actually create some positive charges and then they neutralize the negative space charge or the negative the charges which are there in the space. Okay. Then the motion of the electron is again it is not hindered. So, it flows nicely from the emitter to the collector. And another thing is that the optimization of the distance between the two electrodes is important. So, the one thing is that flow cesium vapor neutralizes space charge, and another is optimize the the distance between cathode and electron, so that your space charge is minimum. Briefly explain the device related requirements of a thermodynamic thermoionic device. Okay. So, what are the device related requirement? So, when we want to make a thermionic device, what are the things we look at? We look at the work function of the emitter, work function of the collector, okay. Then very important thing is their stability at high temperature, because I mentioned that in order to generate more current or in order to make the thermionic emission device efficient, one has to raise the temperature. Therefore, stability, thermal stability is very important. Similarly, chemical stability is important. Okay. And in some cases, what is done for a thermionic emitter which is used in a thermionic device, a negative electron affinity surface is generated or created, negative electron affinity. NEA. Okay. And I have discussed a little bit about what is negative electron affinity and how it improves the thermionic emission process. So, these are some parameters which we have to look at very critically for a device, and of course, another point is the thermal conductivity. Heat should be, whatever heat energy is given to the through the material, it should be conducted efficiently. So, these are the few things which one has to take care when design and fabricate a thermionic device. What are the key components of a thermionic generator? So, we have seen the thermionic generator is basically it is in diode geometry, that means 2 electron geometry. Okay. So, the key components are the emitter, the collector, and the inter-electrode separation. This is a very important component. And number 4 is the circuit, which is connected outside these 2 electrodes. Okay. So, these are the important components of a thermionic generator. Now, let us look at what are the advantage of refractory metals as thermionic cathode. So, you know the refractory metals are the first choice which people have when started making the thermionic generators. So, what are the refractory metals? Like tungsten is a refractory metal. So, why these refractory metals are used? The most important thing is that the refractory metals have very high melting point. Okay. So, due to high melting point, one can go to high temperature for refractory metals for emission of electron. All right. So, the first characteristic of a refractory metal is high melting point. Okay. And the work function is, of course, for refractory metal the work function is not very low like some other materials like hexaboride, the work function is low. For refractory metal the work function is not that low, 4 to 5 electron volt is the typical work function, but one can optimize the work function for refractory metal, okay, for a good emission. So, work function stability of this material, particularly at higher temperature. This is important. Thermal stability, chemical stability, they are very good for refractory metals. Okay. And of course, the thermal conductivity. This is another very important the property of refractory metal for which they are used as thermionic cathode. Next question, what are the important properties of collector materials in thermionic device? So, in the collector materials also we know that their work function should be low, again their stability also should be high, particularly because electrons are continuously bombarded on the collector material. Okay. So, there could be erosion of material from the collector because of continuous bombardment of electrons. So, they should be stable, or what we call that less probability of material erosion, or this is known as sputtering. We have already discussed what is sputtering. Okay. And third is their surface property. Surface property of the collector material should be very good, because they have to accept the electrons. So, their surfaces should be, I mean, they should be made, or their surfaces should be good, that electrons can be easily collected to this collector material. Apart from that, they should also have all the stability, again the at high temperature, because the entire environment is at high temperature, they are continuously getting bombarded with electrons. So, temperature is generated there also. So, they should have a good stability for high temperature and also good conductivity. Okay. So, these are important properties of the collector material. So, what is field enhanced thermionic emission? Okay. What is the advantage of such emitter? When we talk about field enhanced thermionic emission, that means I have already discussed the thermionic emission, which is driven by the heat energy. Okay. And then I also discussed about the field emission, which is actually driven by the electric field. It is a cold emission process. Now, if you combine these two, thermionic emission as well as field emission, that means you are taking advantage of both the energy sources, heat energy as well as the electric field. Okay. So, you can have an enhanced emission. So, emission will be due to thermionic process, which is temperature driven, and then we have extra electrons coming out, okay, because of field emission or field emission process, which is field driven or electric field driven. So, I have now large number of electrons emitted. So, a set of electrons will be emitted due to the thermionic emission, which are temperature driven, and another set of electron will be produced by field, okay, electric field, which will come out due to quantum mechanical tunneling process. Okay. And then we have more number of electrons. So, if we want to increase the intensity of any electron source, that means if we want to increase the number of electrons from any electron source, okay, which are very important for an electron microscope as well as for X-ray source, we should have both the processes simultaneously working. Okay, let me just now review this chapter with few more questions. Okay. What is the difference between thermionic emission and secondary electron emission? So, what is thermionic emission? Again, it is a temperature driven process, or the heat energy is supplied and electrons are emitted. What is secondary electron emission process? Secondary electron emission process is where electrons strike any surface and then it goes inside and generates some secondary electrons very close to the surface, and the secondary electrons come out. Okay, that is called secondary electron emission. So, you need a primary electron before you generate a secondary electron, and this primary electron interact with the material close to the surface, and then they actually generate secondary electrons which are emitted, and this is the technique which is used for SEM. Can a thermionic electron source be used as a electric energy generation? So, we have seen one can have a configuration, very simple diode configuration, where we have an emitter, we have a collector, and the electrons are emitted from the emitter, they are getting collected in the collector, and then these electrons are coming back through the circuit through a load resistance. Okay. So, there is a voltage drop across that or the output voltage, and this output voltage can be generated as in can generate electric power. So, I have defined all these quantities, and therefore, the thermionic this device can be used as a electric energy generation or electric energy generator. Draw a typical diagram indicating energy levels of a thermionic source in diode configuration. So, I have already shown it to you. So, what energy diagram you consider? You consider a Fermi level of the emitter, the vacuum level of the emitter. This is the emitter side, and then you have a Fermi level of the collector and the vacuum level here. This is the collector side. Okay. So, this is phi E, this is phi C, okay. And the difference between phi E and phi C is actually the voltage out if you have a load connected here. Okay. All right. So, this is a typical energy diagram of a thermionic emission device. What is the role of the electrode gap of a thermionic device? This is a very important the component of a thermionic device, because there is a anode, there is a cathode, there is a anode, that is there is a emitter, there is a collector in between this gap. So, the optimization of this gap is extremely important. Okay. The important in that sense that if I increase a gap, it will it will flow will be, although the electron flow is same when I consider emitter material at a particular temperature, but many electrons will be lost. Okay. And if I reduce this distance too much, it can also generate the space charge effect, and the electron can be very highly bombarded to the collector material, and therefore, there may be a damage of the collector material also. So, one is to optimally look at this distance, so that the space charge is also minimized, the damage of the collector material is also minimized, and the electron loss is also minimized. Okay. So, all these three things are to be considered properly before we optimize the distance between the two electrodes of a thermionic device. Why low work function is an essential requirement of a thermionic source is very simple. So, we can see from this. So, if our work function is less, emitter material as well as the collector material, if emitter material work function is low, we have a high emission probability. If collector material work function is low, then the difference between the work function of emitter material and collector material becomes high, and then we have more output voltage generated. So, it is extremely important that the work function of the emitter and the collector material should be optimized before we design a thermionic generator. in a thermionic device, which are the major component of the heat involved. Okay. So, if you remember that we discussed there are various components of heat in a thermionic device. What are the important components of heat? The first component is anyway the heat which are generated or which are being supplied to the emitter. This is the first component. Okay. Second component is the heat which are actually conducted towards the collector. So, how heat is conducted? Because electrons are taking energy from the source and they are actually flowing towards the collector after emitted from the emitter, and they are actually the heat are conducted through them. So, the first is the heat Q in, which is coming from the input source. Second is the Q conducted, which are actually conducted by the electrons and going towards the collector. Okay. And then Q radiation. Okay. Because any hot body can radiate because of its higher temperature. So, Q radiation is a very important component, and then all the circuitry which are connected, so wire, lead, etc. There is a Q lead. Okay. So, as current is passing through the circuit, there will be a loss of heat or the Joule loss. All right. And if we put any cesium vapor in that, they will also conduct heat. So, we have another heat component is Q cesium. Okay. So, let us go to the next question. What are the advantages and disadvantages of oxide coated materials as electron emitter? So, oxide coated material, we have seen the importance is that their work function is actually very low. So, when we consider refractory metal, their melting point is high, but the work function is also high, okay, higher. So, if we have an oxide coated material, their melting point is relatively low, but their work function is quite low as compared to refractory metal, and therefore, the oxide materials are used. Like in the next question, why thoriated tungsten is better than tungsten as an emitter? Because when we make it thoriated, there is thorium oxide to the tungsten, then we can lower the work function significantly. Okay, because of this coating. All right. So, it can work at higher temperature because its melting point is high, but the work function is significantly reduced, therefore, the emission probability will enhance. What is negative electron affinity surface? Give an example in the context of thermionic electron source. So, I have already discussed with you what is negative electron affinity surface. So, when we talk about the electron affinity, when we talk about the electron affinity, it is basically the difference between conduction band and the vacuum level. So, generally this difference is positive, okay, the kappa value is positive, but one can also shift the vacuum level below that conduction band. In that case, the electron the energy becomes, or this chi value becomes negative, that is called negative electron affinity surface, and therefore, the emission enhances. And we have seen one example that when the diamond, generally it is a positive electron affinity surface, but when we put hydrogen in that, okay, it actually creates a negative electron affinity surface. Okay. So, this is discussed in the lecture. how this the hydrogen in the diamond, it gives a negative electron affinity surface, okay, and it can enhance the emission probability. How field enhanced emission is possible in nanostructured material. So, this also we have discussed, because in nanostructured material what is done, actually we make a very sharp nanostructure. Okay. Typically when we make this material, it is something like this. So, what we use a sharp material nanostructured, and then we can also have a low work function coating. Okay. So, that will enhance the electric field as well as the emission probability. Okay. So, we have, because of low work function, we have higher probability of electron emission, and because of the sharp nature of the emitter, we have higher electric field, and it can give more electron due to field emission process. Okay.